So we started the discussion about friction. Friction. Everybody's listening. Okay. So we started talking about friction. And to summarize, this is what I said. In statics, we basically are dealing with two cases when it comes to friction problems, right? Case one is that implicitly or explicitly, right? The problem states that equilibrium, exists. The object is not moving, no slippage is going to take place, like that ladder problem we did, right? That for whatever way it is stated, it directly or clearly implies that no motion is going to take place, and this structure, piece, whatever, is in equilibrium. That means the force of friction that develops at that point of contact, or the potential slippage between the two pieces, is going to be a maximum that mu s, coefficient of static friction, times the vertical load that develops perpendicular to the potential direction of motion. Okay, so that's case number one. Case number two is that, basically you do not know if equilibrium, is satisfied, or the conditions of equilibrium are satisfied, or the object may or may not move, or the slippage may or may not take place. In other words, we do not know the value of this. We know the friction force exists, but we cannot say if it is the maximum value, which is mu sub s, or not. In other words, this f of f, may be less or equal to mu sub n. If that is the case, you have the equilibrium. If this f of f is greater than mu s times n, you have motion which is pending. So in other words, you need to verify equilibrium. So what is the main difference between the two? As far as the analysis goes, not much. You need to draw the Freebody diagrams and apply equations of equilibrium, except that in this case, f of f is not an independent force, because its value is a function of n. So no additional unknown force comes into the picture, right? Here, f sub f is an unknown, meaning that basically an independent force. It is not related to mu s. We do not know, right? So you have an additional force that comes into the picture, or comes to the Freebody diagrams, right? So you need to find that and then confirm which of these two cases exist. So that's one thing that is very important to know. That's the first piece of information that you really need to in order to solve friction problems. The next thing is basically the procedure, is very similar to the way you did the frame problems, okay? So not big of a difference. All you need to do, okay, you need to identify, obviously, step one, you need to identify case one or case two. Which of these two cases you have? Given the information in the problem. You draw Freebody diagrams, okay? That's very similar to the frame problem. The only difference is that you do not need to find all unknown forces, only the one that the problem states or wants you to find. That's the only case you have, okay? So these are really the three important steps that you need to be able to identify. There's also, of course, another probably side sort of a point that is important, and I write it actually in a different color, or maybe put it as an asterisk. In doing these free body diagrams, this is related to this case. When you do the free body diagram, be careful or know that the direction for f of f is not like, again, frames that you make the assumption, and if it came out to be negative, you correct that. You always can figure out the direction for the force of friction. It's always opposite to the potential direction of motion. So basically, for the lack of a better statement or word, this is really the guiding, these are the guiding principles to solve any friction problem, okay? Any questions on any of these? So I did one problem using case one. Let me do more problems, and then we do a few more on case two. I want you to really become mastered at, I don't like this word master. It's one of those bad words in English language, right? When you say master, inherently or implicitly, you expect somebody is a slave, right? But anyway, so that's the political statement of the day. Okay, so let's do this problem. Okay, let's say you have a frame problem like this. It's made of two pieces. It consists of a disc that is pinned to a bar at point A. Radius of this disc is given as r 0.2 meters. So this disc is residing along this inclined surface that makes an angle of 30 degrees with the horizon. Let me label all these. Okay, it is pinned at this other end at a point B, and between the coefficient of friction between the disc and this surface is given as static coefficient of friction is given as 0.2. We want to find if we apply a load P at this point, which is given at the distance of 0.3 meter from A and 0.6 meters from B, okay, what should be the maximum P that, as the problem states that, in other words, how large this force can be that still this disk does not slip along this surface. So maximum force P that yet doesn't cause a slippage of the disk along the surface. In friction problems, as I said, the first and most important thing is you need to read the problem statement, and as a step one, identify whether you have case 1 or 2. So the minute you hear that no slippage is going to take place, no motion is going to take place, that means it's case 1, right? So you have equilibrium. As soon as you know it is case 1, then you draw your free body diagrams accordingly. So I have this free body diagram for the disk and the free body diagram for the bar. But as I said, when you draw the free body diagram, be careful when it comes to the direction of the friction force. It's always opposite to the direction of motion. If this disk is going to rotate or slip, this force is going to cause this to push down, or the A goes down, so the disk is going to rotate like this. So if the motion of the disk is like this, the friction force at C acting on this disk would be in the opposite direction of that motion. Motion takes place like this, right? So if it's going to go like this, or moving that way, the friction force then would be like this, right? And obviously, the normal force would be normal to this plane. By the way, weight of this disc is also given. The weight is 35 kilogram times G, and assuming that G is gravitational acceleration is 10 meters per second squared. So you have this force W. So let's say that is 350 Newton. At point A, you have AY and AX. So on this bar, you have two forces equal in magnitude, opposite in direction. You have the applied load, and you have this BX and BY. So you drew a free body diagram, you put the consideration of what direction this force will be. Then the last thing to worry about is you need to find the unknowns, but do not worry about finding all the unknowns. That's the biggest difference between the case of frames and friction problems. You don't have to, if you want to, you're more than welcome, but always listen what the problem is asking, so only find those unknowns that you've been asked to find, which in this case is P, right? So I look at these two free body diagrams, and based on that information, I consider these two free body diagrams, and I would say, okay, let's find the unknown P. So I will start with this free body diagram, since I can see easily, okay, that if I take summation of moments about B, this, and this force are not going to appear, and I can find a relationship between P and AY, and if I go to this free body diagram, just by taking summation of forces along Y, I can find N, which F is also related to N, so you have only one unknown here. So all I need is just this unknown. So let's do that. So I'm going to go here, take summation of moments about B is equal to 0. So I have P times the distance 0.6 meters, right? And then I have minus AY times 0.9 is equal to 0. So AY would be 2/3 of P from this free body diagram. I don't care about the other unknowns. I just leave them. Okay? So I go here now to this one, if I write summation of forces along y is equal to 0, I have negative ay, which is negative 2/3 of p, right? Plus, this is what? This is 30 degrees, right? So this is 60 degrees. This is 30, okay? This is 30 degrees, right? And this is 30, this is 60. Okay, so that you can easily keep track. So summation of forces along y will give me what? N cosine plus n cosine of 30, which is square root of 3 over 2, okay, minus f, which since we know this is not going to move, f is mu times n, or mu s times n, and mu s is, of course, is given as 0.2, okay, right? Cosine of 60, which is 1/2, is equal to 0, okay? So let's simplify this. This is 1.74 divided by 2.87 minus 0.1, 0.77. So n times 0.77 is equal to 2/3 of p.
How about the weight? Yeah, the weight of that.
What is it?
The weight of the...
Oh, yes, you see, that should be equal. And I forgot to include this. So minus 350, so this is going to go to the other side. So I have this minus 2/3 p, right, is equal to, okay, 350 Newton, sorry, okay. Let's now take summation of moments about point O. That's what I would do, okay. So take summation of moments about point O is equal to 0. So this goes through that. So all I have is this force, F of F. This is the vertical distance, which is given. That's the radius of that, which is 0.2. So I have F of F, which is again mu times n, or 0.2 times n, times the distance 0.2, moment of this force, okay? This goes through that, so you have just negative ay times distance 0.2 is equal to 0. So again, you can substitute for ay, right? So if you substitute for ay, which is 2/3 of p, right? So you have two equations in terms of p and n. You can solve for p. P comes out to be, I have the answer here, 182 Newton. Do you need to find n? No, problem didn't ask for that. So remember, in these friction problems, just find those unknowns you've been asked to find. Save yourself time. Do not do extra work. Okay. Any questions? No. I'm going to do another problem. Okay. So let me erase this. Oh, this seems to be a much more efficient eraser. Okay. This is from your student success fees that you paid, right? You paid 75 cents to buy one of these, no? Which is not bad. Okay. All right. So you have no question, by the way, about the exam coming up. You know, there is one problem on 3D rigid body equilibrium, one on moment of inertia, and one on frames. Just in case that if you didn't read my emails or Okay, so let's do another problem here. Let's do another problem of case 1. Okay. This is so relevant, this problem, given all the storms we've had on the East Coast and the advanced infrastructure that we have for power transmission, which is envy of the world, right? These old archaic wooden poles. Okay? So we have this guy, maybe he works for PG&E, who's been asked to get up there and fix this, power line. So the guy wears his shoes. Let's see if I can do a good job drawing this guy. Okay, not bad. The center of gravity of this guy is right here. So he's got this belt that he wraps around the pole and goes up, right? And the problem is, statement is this. We know that he's wearing some good shoes, so at this point of contact between his shoes and the pole, there is a coefficient of friction of static coefficient of friction, 0.6. And this guy weighs 180 pounds. Distance between this point of connection of the belt to this, cable, whatever it is given. So this distance is 2 feet. This is 0.5 feet, and the thickness of this pole is 0.75 feet. Okay. So the problem statement is, if you've been hired as a consultant, this guy has hired you to tell him if in his negotiations with PG&E, okay, what kind of belt you should ask them to buy for him so that he wouldn't fall off. The information that you need to provide him is what is the coefficient of friction that is required here to keep this man in place. So listen to the problem statement, which is very easy. The objective is you want to save this man's life, so he should not slip down the pole. Or this belt or his shoes would not allow him basically to slip down. But that means what? In a statics language, that means what? Case 1 or case 2? Case 1. So you're being told this man is going to be safe and sound as he's climbing this pole. He's not going to slip down, so he's going to stay there. The only thing is, you want to know if you want to keep this guy stable in equilibrium, what should be the coefficient of friction here? That's all. So all you have to do, again, you answer the question 1, right? First of all, you have case 1. That means both at point C and at point A, force of friction is mu S times the corresponding NA or NC. So then you need to draw the free body diagram. And I would put here, consider direction of the force of friction. And then apply equations of equilibrium. Find only the unknowns that you need to find equations of equilibrium that will give you the unknowns. Okay, so let's start with 1. And to save time, I'm just going to draw the free body diagram. I'm not going to redraw all these. I didn't do a great job, artistic job, to draw them anyway. So, but you want to draw the free body diagram. In drawing the free body diagram, you need to consider this. If this guy is going to, God forbid, slip down, what direction he's going to move? Downward, right? So that means motion takes place in this direction, therefore the friction force would be like this. Same thing here. If this slips, this belt would slip downward, so the force of friction at A would be like that, right? Then you have a vertical or normal force perpendicular to that direction of motion, and obviously this is pulling this way, so there is a force of NA in that direction. You don't have to know the correct direction for this, because once you solve the problem, it will come out to be negative, and you know that you have to change the direction. But that's the free body diagram, right? And we addressed this in drawing the free body diagram. So now let's use just the equations of equilibrium. So what I would do, I would first take summation of moments about point A is equal to 0. Okay. So you have negative 180 times the distance from here to there, which is 2.5, right, plus 0.75. So you have 2 plus 0.5 plus 0.75. Intentionally, I write them separately so you know how I found that distance, right? So that's negative clockwise. Then you have this force, so that force would be positive F sub C times 0.75, okay? That's it, is equal to 0. So you get F sub C comes out to be, okay? In fact, F sub C obviously is mu CS times N, right? So we get an NC. And C comes out to be 131.46 Newton.
Do you not have to include NC in that?
I'm sorry? For the free body diagram? Yeah, I had this one, then I had this one, right?
Right.
Yeah, I did include that. Did I not? That was F of C times 0.75. About moment about point A.
What about NC?
Oh, NC, yes. What am I doing? I have NC also times, this distance is given. I forgot to give it to you. This distance is given as 4 feet, so this is NC times 4. Well, that's the answer, because I have the answer. The answer is correct. Okay, so once you have that, right, you just simply write summation of, either summation of force along X or Y, doesn't matter. So I have that answer here. Summation of forces along X is equal to 0. So you have NC minus NA is equal to 0. So NA will be the same, 131.46 Newton. Okay? Then you write summation of forces along Y is equal to 0. So you have FA plus FC, which is 131.46 times 0.6, right? Minus 180 is equal to 0. That will give you F at A is equal to 101.1 Newton. So the force of friction would be 101.12. You do not want slippage take place. That means that force is a maximum, static friction force. So this should be equal to mu at A, which is what you would want to find, times N A, which is 131.46. So that will give you mu at A, which you can find to be 0.77. So in order for that guy not to slip, he needs a belt that has a coefficient of friction, or generates a coefficient of friction between that and the pole, 0.77. Any questions? So that's type 1 problem. Yes?
How did you go from 180 pounds to newtons? Did you convert it?
Why should I get newtons? Should be everything is pound. So what is the answer? That means I was careless, right? Everything was in pound. Of course, you know, one of the reasons for that, right? My passion and respect for Mr. Newton, right? That I told you about at the beginning of the class, right? Any other questions? Okay. All right, so let's now, so we have done 3 problems for case 1, right? So let's now look at case 2. I'm just categorizing it that way, but frankly, the procedure, complexity of the problem, what you are asked to find is not much different. So procedure is, again, right, draw the free body diagrams and find the unknowns. So let's do, in fact, a problem which was given as an exam problem. In fact, was a final exam problem. It's a simple problem. You have a mechanism that is used as a brake mechanism to stop a rotating disc, okay? That is subjected to a torque of 5 Newton meter. You want to stop that, so you design this brake mechanism that is attached to a pin here at point A, and you apply a load of P to stop this disc from rotation. Okay. Let's first give you all the distances you need. This is 0.2 meters, this is 0.4 meters, and the distance from this surface of contact of that brake to this pin is 50 millimeters, okay? And the radius of this disc is 0.15 meters, and this is massless. Okay. So the problem statement goes like this, that you know that the coefficient of friction at point B, coefficient of friction here, okay, is given as 0.3. You want to know, okay, you want to figure out how much force you need to apply in order to stop this or to break this disc. You want to know which one of these two forces, P of 70 Newton or 30 Newton, is adequate. In other words, this force is unknown, and you want to find out if these values, potential values for these, will cause the stoppage of this from rotation. All you know there's a friction force here, right? But you do not know if under these two forces, that friction force would be adequate to stop this disk. So the equilibrium is in question. You do not know if for sure these values will stop that disk. So you need to verify equilibrium. So this is case 2, that you need to verify equilibrium, okay, and find whatever unknown the problem has asked you to find. So procedure as far as the steps to follow are the same, right? You have a disk and you have a bar, you just draw free body diagram of both, right? So again, this is the disk, but this disk is connected here to point O, so there are two reactions here. This is subjected to a moment or a torque of 5 Newton meter. So if this disk is moving that way, or rotating that way, or the motion or the direction of motion is this way, what direction would be the direction of the friction force at point B? That way, right? Motion is this way, so this is force at B. And obviously you have, of course, this vertical force at B. So correspondingly, at this point, you have this force B, friction force B, like that. And at A, you have these two unknowns, AX and AY, and then you have this applied load P. So you have these two free body diagrams. So we, as a step 1, we decided which case it is. As a step 2, we drew the free body diagram with the understanding that what potential direction the motion may occur. So we can draw the free body diagram correctly or identify the direction of the friction force properly. The third step now, apply equations of equilibrium. So again, I have two free body diagrams, 1 and 2. Let's consider 1. And remember, again, emphasizing, you do not have to find all the unknowns, only the ones that you need or you've been asked to find, which is force P. So I'll take summation of moments at point O is equal to 0. In other words, assuming that this is not moving, right? The maximum force of friction that would be generated here is what we are trying to find. So if you take summation of moments about point O, this goes through that. So you have 5 Newton meter, right, minus F sub B times 0.15 is equal to 0. FB comes out to be, I have the answer here, is 33.33 Newton. If this is the maximum friction force, right? In other words, the force, maximum force that allows me to use the assumption that this moment or this torque is not going to be able to rotate this. That means this FB would be mu at B times N at B, right? Coefficient of friction at that point is given 0.3, right? So this is 33.33. So NB comes out to be 111.1. So now I go to this diagram, okay, based on that information. to find P. So I will take now in the second Freebody diagram, take summation of moments at A is equal to 0. Okay, I have N, B, okay, generating a negative moment times that distance 0.2. Okay, this distance between here and here was given 0.05. Okay, so I have positive FB times 0.05, and then you have plus P times 0.6 is equal to 0. So you substitute for these, okay, for NB and for FB, which you have here. That will give you P, which comes out to be 34.26. So if you have a force of 34.26 maximum, right? Okay, that means what? If you apply a force of 30 Newton, is this going to move or is this going to stay stable? What you think? Is it going to move or? It's going to move because it's less than 34.26, right? But for the 70 Newton, which is much larger than 34.6, okay, this is going to cause no motion, right? Okay. In other words, that's what the unknown that the problem is asking that you found. Okay. So that's easy, right? We have another 5 minutes. Let me see if I can, if I have the, if I have a problem that I can do it in 5 minutes or not. Probably not, because this is gonna, all the problems I have is gonna take more than that. And in the other section, I could actually hardly do 3 problems, so at least here we could finish 3 problems. So with that said, wish you luck on Friday.